So I finished marking question 4 today, the algebra question. I thought we should probably go through that some. So we have 3 positive real numbers, a, b, c, greater than 0 with bc in 1, 2 with, what's it?
A plus A plus B, B C plus B times C plus 1. A plus C over C B plus 1 equals
2. And you prove that you can make a triangle from those with lengths of those sides. Okay? So the first step that we expected everyone to do, which we were quite surprised that not that many people did, was that whenever you have fractions like that, it's always a good idea to get rid of the fractions. So if you multiply both sides by b times c plus 1 times c times b plus 1, you get a plus b times c times b plus 1 plus a plus 1 times b times c plus 1 is 2 bc b plus 1 times c plus 1. And you simplify this to get c ab plus a plus b squared plus b times ac plus a plus c plus 1. Thank you. So ac squared plus c is 2bc times bc plus b plus c plus 1. And you expand this further, you get abc plus ac plus bc plus b squared c plus abc plus ab plus bc squared plus bc equals 2b squared c squared plus 2b squared c plus 2bc squared plus 2bc. So that's quite a mouthful. But then you get to this point and you see, okay, you've got a BC over there, which cancels one of the BCs over here. So that becomes a single BC. You have 2 ABCs over here, so that becomes 2 ABC. You have an AC over here, which should cancel something, never mind. See, there's a BC there, go over there, and then there's a BC squared over here, which cancels with one of these. So then there's a B squared C over here, which cancels with one of these, and you're left with 2 ABC plus AC plus AB equals 2B squared C squared plus B squared C plus BC squared. Okay, so you get to that, and at this point you notice that on the left you've got an A in every single term, and here each term has a BC in it. So you try to factorize it, see what you get. You get 2 A times 2 BC plus C plus B is equal to BC times 2 BC plus B plus C. And you have these two factors in common. And since you're given that B and C are going to be greater than or equal to 1, you know that 2BC plus B plus C is going to be greater than 0. So you can divide through by it without having to worry. So you get that A is equal to BC. For any choice of B and C, that is the A value that will satisfy this equation over here. So if you got to this, you would have gotten 2 out of 7. Okay, so then the next step is how do you use this? Yes?
But if you drew the triangles, how much did you get?
5.
So the problem is that you can't just draw a few triangles and claim that that's a proof. You have to rigorously show that no matter which BC you try to use, that will always form a triangle. So here you get A in terms of BC, so you can just choose whichever B and C you want and use that.
I got it didn't form a triangle for one, where B and C were both 2.
Okay, so
It can't be 2.
if B equals 2 and C equals 2,
It's excluded.
then by the definition of this closed open subset, we need 1 less than or equal to B and C less than 2. So if you let them be 2, it won't. Yeah.
You get it marked right in math.
Okay. So the next step comes into play with what we're going to be doing today, which is inequalities. So there's this useful thing that comes up quite a lot in geometry. If you have a triangle with lengths A, B, and C, so a triangle is just 3 points in the plane, right? What's the shortest distance between these 2 points? It's a straight line. So the distance, okay, let's say A, B, C. The distance from A to B, the size of AB, which is equal to C in this case, is that would be the shortest distance between A and B. So any other path that you choose will have to be longer than that. In particular, if you went from A to C to B, that would be a longer path. So you get C has to be less than A plus B. And this is known as the triangle inequality. So from here, you notice that the choice of A, B, and C doesn't actually matter. So you get 3 different inequalities that have to be satisfied at the same time. You have that A is less than B plus C, but B has to also be less than A plus C, and C has to be less than B plus A. And only when all 3 of these are satisfied is that sufficient to prove that you can use those A, B, and C's to make a triangle. Okay? So the way you go about this is simply by replacing A with BC into all of these things. So 1, let's call this 1, 2. 1 is equivalent to BC being less than B plus C. 2 is equivalent to B being less than BC plus C. 3 is less than C being less than BC plus B. Okay? So at this point you only got 2 variables that you're working with, which makes it a bit easier. Because here again you factorize it and you notice that BC plus C is just C times B plus 1. And here, this is B times C plus 1. So for these 2, we'll do that one separately. So you need to show that B is less than C times B plus 1 for all B and C that you choose in that interval. So in particular, you notice that since C is bigger than 1, or bigger than or equal to 1, because it's in that interval, you need that C times B plus 1 is greater than or equal to B plus 1. Is everyone okay with that? And then from here, you can show that, well, B plus 1 is always bigger than B, no matter what you choose, which means that this statement is true, which means that this statement is true. And okay, you can do the same argument for this one. So if you do these two together, you would get 4 out of 7, I think. And the last one uses a bit more work. So you need to prove that BC is less than B plus C. And this is equivalent to BC minus B minus C being less than 0, which is equivalent to BC minus B minus C plus 1 being less than 1. Right? Just add 1 to both sides, it's still the same thing. And again, you try to factorize because you have this expression that you can't do anything with except factorize. So you, after some playing around, you might find this. You can check those two are the same thing. And here, you notice that, well, 1 is less than or equal to B is less than 2, and 1 is less than or equal to C is less than 2. So 0 is less than or equal to B minus 1 is less than 1, and 0 is less than or equal to C minus 1 is less than 1. So if you multiply these two together, since it's all positive, you can multiply the left terms, the middle terms, and the rightmost terms, and you get that 0 is less than B minus 1 times C minus 1 is less than 1. Which means that that statement is true, which means that is true, which means that this one is true, so all 3 of these are true, which means they must form the sides of a triangle. And that would have gotten you 7 out of 7 today. Okay. It was a question 4, so it does need a bit of work. But yeah. Okay. Everyone okay with that? Anything up here? Okay. So we've already covered one inequality, triangle inequality, but that's not the most important one, because there's only one inequality that you ever need to know, which is first place value. Cool, so that's the lecture for today. So this says that, I should say, for all x reals. So this says that no matter which values of x you choose, that value squared will always be 0 or a positive number, and will only be 0 when x is 0. Okay? So, I mean, that seems like that's such a short statement. How can that be useful? Well, then you start to get things like, okay, well, prove that a squared plus b squared is greater than or equal to 0. And you can do this by seeing that, well, a squared is bigger than or equal to 0 because of this, and b squared is bigger than or equal to 0 because of this. And you can always add inequalities together. So a squared plus b squared is bigger than or equal to 0, which proves that. Yes?
Even though it's bigger than 0, it's not the most restrictive inequality for a squared plus b squared.
Yeah, no, by no means. So this 0 is staying constant, whereas a squared plus b squared is varying as much as you want. So saying something like 100 squared plus 1,000 squared is bigger than or equal to 0 isn't really profound, because clearly that's just true. So now you can change things up a bit. And you get stuff like prove that a squared plus b squared is greater than or equal to 2ab for all real values a and b. So this one is quite similar. Yeah. So if you haven't seen it, what you do is a squared minus b plus b squared minus 2ab 0. So these two things are equivalent statements. And, well, you can just rearrange this to get a squared minus 2ab plus b squared is bigger than or equal to 0. And from Monday's lecture, you should recognize that as a minus b squared bigger than or equal to 0. And from that's just clearly true, because a minus b is some real number, and this theorem tells us that any real number squared is bigger than or equal to 0. So if you follow these steps back, you can derive the statement. So this is a much stronger inequality than this one, because 2ab could be really close to a squared plus b squared. So if you choose, I don't know, a equals 2 and b equals 1, then you get that a squared is 4, b squared is 1, so it's 5 is greater than or equal to 4, which is a lot better than saying 5 is greater than or equal to 0. So sometimes with more difficult or more complicated inequality questions, you could, one strategy is if you have to show that some function f of x is bigger than or equal to g of x, where those two have some expressions that are very complicated and horrible, then if you can show that there exists some other function h such that f of x is greater than or equal to h of x for all x, and that h of x is greater than or equal to g of x for all x, then can you see that that would be sufficient to prove that f of x is greater than or equal to g of x? Yes? No? Okay, I'm seeing nods. Okay. So this technique of moving stuff to one side and making them squares is known as proving by first principles, because you derive it down to something like that, and then it's very clearly true when you write it in that form. Okay, yes?
Are you saying that all inequalities kind of are reducible to a square being greater than naught in some way?
I wouldn't say every single inequality. For instance, the triangle inequality isn't directly, but for most Olympiad questions, you can use some clever argument to reduce it to some x squared greater than or equal to 0 for a clever choice of x. Okay, so there is a, before that, does anyone have yesterday's question paper with them?
Oh, that question.
Yeah, so,
X squared plus 5y squared plus z squared is greater than or equal to
something like that.
I think it was 2y plus 2y plus 2x plus z. I think it might have been that.
yeah, it is.
The x and y was
It's 2y plus z. 2y, 2x plus z, so yeah.
So, for this question, the way that was intended to do it was, okay, you have some product of things that don't seem to be particularly useful, so try and multiply them out and see what you get. So you get that this thing has to be greater than or equal to 4xy plus 2yz. Okay. Now you have something with some squares on that side and linear terms on this side. So you think maybe you can get x squared greater than or equal to 0 from something. So if you want to use that, you need a 0 on one side. So the nicest side would be to make this side 0. So to do is you move everything over to one side, and you get the statement is equivalent to x squared plus 5y squared plus z squared minus 4xy minus 2yz being greater than or equal to 0. Okay. Now you have this mess. And here you see you've got 2yz and a z squared. So maybe you could force out a y squared somewhere and make that a square. Okay, but you have 5 y squareds over here, so what if you borrow one of them and change this to be plus 4y squared plus y squared? So you have a y squared, a z squared, and a minus 2yz. And now you notice you have an x squared, a 4y squared, and a minus 4xy. At which point you remember your factorizations and see that this is equivalent to x minus 2y squared plus y minus z squared being greater than or equal to 0. At which point you have a sum of two squares that need to be greater than or equal to 0, which, well, that's just true by that theorem. Okay, so this is an example of how you would use it in a question. Right.
Question.
Yeah.
Given that a squared plus b squared is not the strongest inequality of the sum of two squares,
Yeah.
does that mean that the original inequality was not the strongest inequality?
No, by no means. So you could. Okay, we'll get to the next thing.
Sure.
You'll see it appearing. So sometimes for inequalities, it's useful to know when the equality condition is true, which is that gives you an idea of how strong that inequality is. So, for instance, if a squared is bigger than or equal to 0, with equality only when a is equal to 0, right? But that gives you a degree of freedom of all of the real numbers except for 0, and so it's not that strong. Whereas something like a squared plus b squared greater than or equal to 2ab, that was equivalent to a minus b squared being greater than or equal to 0, which is equivalent to a, well, this will have the equality condition of a minus b equals 0. So when a equals b, it's the only time when equality will hold there, which seems a bit stronger than just not being 0. Or, well, only having equality when a is 0. So the next thing is similar to this. I'll rewrite it. So consider something of the form a squared plus b squared being bigger than or equal to 2ab. So it turns out it's also true that a cubed plus b cubed plus c cubed is greater than or equal to 3abc. And it turns out that a to the 4 plus b to the 4 plus c to the 4 plus d to the 4 is greater than or equal to 4a, b, c, d. Okay, and which is?
If we want to use that in Olympiad, can we just say it as a fact, or do we have to prove it every time?
If it's something like that, just prove it, but I'll give you a theorem now that you can claim, and yeah, it just tells you that these are all true. So you start to see a pattern emerging that these exponents are the same as that coefficient over there. there's something called the
No, that's basically AMGM, like what I was out of school.
Okay. So the arithmetic mean geometric mean inequality says that if you have A1, A2, A3 up until AN being greater than 0 or greater than or equal to 0, where all of those values are real numbers, positive real numbers, then A1 plus A2 plus A3 plus and so on until AN divided by N is greater than or equal to the nth root of A1, A2, A3 multiplied together until AN. Okay? So no matter which n you choose, no matter which values of A1 up to AN you choose, this will always be true. So to see how this is equivalent to these statements over here, consider what happens when you let A1 equal A squared and A2 equals B squared with n equals 2. Then the AMGM inequality says that A squared plus B squared over 2 is greater than or equal to the square root of A squared B squared, which is AB. So A squared plus B squared is greater than or equal to 2 AB. Similarly, you can say let A3 equal C squared, and then this changes to be A squared plus B squared plus C squared over 3 being greater than or equal to the cube root of A cube, B cube, C cube, which is just ABC. So you end up with, so these should be cubes. So you end up with A cubed plus B cubed plus C cubed being greater than or equal to 3 ABC by the AMGM inequality. I should maybe go over the name. So arithmetic mean, geometric mean. Mean is another name for average. I'm sure you've seen that in school. So the arithmetic mean is just normal average as you would expect. So like if you have 5 tests and you get 80% for one and 75 for another, and whatever, you find your average by adding all the marks together and dividing by the number of tests that there were. Whereas this one is a bit different. It comes up in geometry, but
So what if we use the geometric mean to average our test marks?
so a nice consequence of the AMGM inequality says that if you use the geometric mean to find your average for all your tests, your average would always be lower than if you just used the normal average. So if your teacher asks you if you want to find your average using AM or using GM, you should always choose AM. Okay. So is everyone happy with this? Yes.
I just want to check, just because the AMGM inequality only holds for positive numbers,
Yep.
that original statements also only hold for
Yes.
positive.
Yes, that's true. Over here, A, B, C, and D are positive real numbers. Should specify that. So on one hand, AMGM is extremely powerful because it lets you take anything of a form like that and solve it instantly. But on the other hand, it's constrained to be only for positive real numbers, whereas proving by first principles x squared greater than or equal to 0 is true for all real numbers. So for yesterday's question, I saw a few people trying to use AMGM to solve that, but I don't think you got the full score because the question specified all possible real values and not just positive real values. So that's an important note. Okay, so the proof of this uses induction. I don't think there's time for that now. So you prove it for all n where n is power of 2, with the idea being that you can prove it for the case n equals 2 simply with, so you have to prove that a1 plus a2 over 2 is greater than or equal to the square root of ab, from which you can see this is equivalent to a1 plus a2 being greater than or equal to 2 square root ab, which is equivalent to the square root of a1 squared plus the square root of a2 squared being greater than 2 times the square root of a1. This should be a1, a2, a1, a2 times the square root of a2. So this is equivalent to AMGM for n equals 2. And you'll recognize this as something we did earlier. It was the second one we did, I think. So you move everything to one side, show that it's a square, so it's always bigger than or equal to 0. So that's how you do n equals 2. For n equals 4, you let a1 equal b1 plus b2 over 2 and a2 be b3 plus b4 over 2. So this just gives you an idea of how you would do it, but it's quite a long proof. So by AMGM, for n equals 2, just using a1 and a2, we get that a1 plus a2 over 2 is greater than or equal to the square root of a1 a2, right? So substituting this in gives b1 plus b2 over 2 plus b3 plus b4 over 2 being greater than or equal to the square root of that thing times that thing there. And if you simplify this, you get b1 plus b2 plus b3 plus b4 divided by 4 being greater than or equal to the square root of b1 plus b2 over 2 times b3 plus b4 over 2, which is in itself less than or equal to the square root of, and you apply AMGM again on that to get the square root of b1, b2, and the square root of b3, b4. So this is greater than or equal to that by doing AMGM on those two terms. And then you can simplify this last part to get, this is just the fourth root of b1, b2, b3, b4, which is what you wanted to prove. So use that idea again for n equals 8 and then n equals 16, etc., etc. And that proves it for all powers of 2. And you can get everything between by making dummy variables that are in themselves the AMs of other sequences. It's just a long proof. You can check it for yourself if you want to. Okay?
Can you just quickly briefly the first question of the process?
First question. Okay, we need one more theorem before we do that. So one last
Tell me what it is.
The power mean inequality.
Power mean.
Yeah. Okay, so there's a generalized version of AMGM.